DeepMind's SL2T. Google just shipped an AI model inside the new Pixel 11 that translates continuous American Sign Language into English text by entirely discarding the raw video feed. Instead of pushing high-definition pixels to a server, DeepMind's SL2T system converts a human into a mathematical wireframe in real time. The local geometry. Processing continuous spatial body movements usually demands heavy video bandwidth and introduces severe privacy risks. SL2T splits the compute pipeline to bypass both. A local on-device model called MediaPipe Holistic scans the camera feed frame by frame, extracting exactly 130 geometric coordinates across the user's face, hands, and torso. The raw camera footage is purged immediately from local memory. Only that stream of moving coordinates gets sent to Google's backend servers. But isolating those 130 coordinates only solves the hardware half of the equation, leaving a massive linguistic roadblock known as the Gloss Bottleneck. The Gloss Bottleneck. Older translation pipelines relied on intermediate tokens called glosses. They assigned a single, fixed text label to an individual hand sign. The research shows that glosses are fundamentally flawed because they strip out non-manual markers. In American Sign Language, a raised eyebrow or a slight torso shift completely alters the grammatical meaning of the hands. SL2T abandons glosses. It maps the incoming spatial landmarks directly to English text tokens. By skipping that intermediate annotation layer, the model captures the full spatial grammar that single-word labels erase. But looking past the linguistics reveals the actual architectural shift driving modern multimodal hardware. The signal under the noise. The SL2T pipeline proves that practical multimodal AI is not about brute-forcing raw video into cloud models. By reducing camera feeds to 130 abstract coordinates locally and bypassing the traditional gloss mapping on the server, DeepMind engineered around the strict latency constraints of real-time vision. For builders and engineers, this provides the blueprint for spatial computing at the edge. You do not need to transmit heavy pixels to achieve complex spatial reasoning. Stripping raw input into mathematical landmarks on local silicon minimizes bandwidth overhead and completely neutralizes data compliance risks. This architectural split, running a deterministic vision extractor locally and a semantic reasoning engine in the cloud, is how heavy models run on mobile hardware. Watch for this exact dual model architecture to become the standard for complex gesture recognition in wearable headsets by late 2026, prioritizing continuous operation over pixel resolution. Subscribe for more